This is Facility Science Podcast number 1. I am Jason Doolittle, and today I'm talking about how the internet works. And I want to do that by defining some of the terminology we use when talking about data networks, so the terminology of IT infrastructure, and then discuss how the technologies described by those terms interact with each other to create the local and global networks we rely on for pretty much everything in modern life, from running our buildings and businesses to our personal communication and entertainment. So before I get into the IT terminology, I want to introduce the concept of layered abstraction, which is fundamental to electronics and computer science and their associated engineering disciplines. So abstraction in this context means conceptually to take a function or a behavior or a concept which might be very complex, define its inputs and outputs, which we can call the interface, and then put that functionality inside a box with the interface exposed outside the box. And this could be a literal box or just a conceptual box. The benefit of this type of abstraction is that it allows us to turn a potentially very complex functionality into something very simple by hiding how it's done and only being concerned about the interface, so that we can use the functionality but avoid thinking about the details of how it works when we don't actually need to care about those details. We can then use that abstracted element, that simple thing that's really complex inside, along with some others to build a new complex thing. Then take that new complex thing, define its inputs and outputs, and put it inside of a box to make it simple. And we can repeat this process over and over, piling layer upon layer of abstraction until we reach our desired outcome. Using this conceptual process, we can create things that are so complex they're impossible to understand as a whole, kind of like the internet, which is what I'm getting at, so bear with me. Another benefit of this type of abstraction is that if we have a well-defined interface and behavior, we can change the stuff inside the box because maybe we find a better way for some relevant definition of better and leave everything else that's outside the box as it is. So let's take an example from building systems and talk about the air handler. We almost always talk about an air handler as an abstract device. It has an interface. Air goes in one end and it comes out the other end with some change in its properties, so something happens inside the box. And there's some mechanism to modify its operating parameters, which is the controls. And it also has some operational specifications, so like its tonnage or BTUs, how much air it moves, its power requirements, voltage and current, energy consumption, and maybe a mechanical shape or form factor. And that's all we need to describe the abstract air handler. Without worrying about what is actually inside, we can understand how air moves through the building, we can troubleshoot problems, and we can even design a system that includes an air handler without even talking about what is inside of it. And we can also interchange any air handler that has the same interface and relevant operational specifications. So we can take one from our favorite brand, one that's more energy efficient, has a lower initial or lifetime cost, or whatever is most important to us when we're choosing a particular air handler for a specific purpose. So a real air handler has some stuff inside of it. It has a blower, which is an impeller and a motor with some kind of drive. It could be a direct drive, a belt drive, gear driven. It could be single speed, multiple speed, or variable speed. It has some kind of cooling mechanism. That could be chilled water or refrigerant coil or something like that. It has a heating mechanism, which could be hot water coil, electric heat. It could be a refrigerant heat pump. It might have dampers and humidifiers and all kinds of other stuff. It also has some kind of controls, and obviously a duct or a passage or multiple for the air to enter and travel through and exit. And we can talk about each of those subcomponents as abstract devices also. Take the blower as an example. Abstractly, a blower has an air intake side and an air output side, and it has some number of speeds, moves some amount of air. We might have a CFM curve or something like that, pulls X amps at Y voltage and so forth. But if we really look inside, the blower is made up of many parts. There's a motor, an impeller, some linkage between the two, some electrical device that drives the motor, and each of those blower components has its own complexity. What is the impeller geometry? Is it fixed or variable pitch? The linkage between the motor and the impeller could be direct or with gears or with belts. How is variable speed or variable CFM achieved? Does it have discrete multiple speeds, electronic variable frequency drive, a gearbox, one speed with some motorized dampers, or something else? And each of the other air handler components can be explored as well. For example, the cooling device could be a refrigerant coil or multiple attached to a complex system of multi-stage condenser towers, or it could be attached to a chiller with water piping and refrigeration. And each of those air handler components could conceivably be replaced with other components that operate completely differently as long as they fit the same abstract specification. I may be belaboring this, but hopefully I'm getting across the idea that we can talk about a very simple device called an air handler, when in reality that device is built up of many complex layers. And we hide that complexity inside the air handler abstraction so that when we want to understand how air flows through our building, we don't have to think about specific details like the pitch angle on the impeller or the stroke volume of the compressor for a particular refrigerant. Now, this might seem overly pedantic for something like an air handler, but it's a little less so when trying to understand the internet. Somehow we have taken a huge pile of literally sand and rocks and metal and arranged it in just the right way to create a high-speed global data infrastructure. It's completely ridiculous that it works, and it wouldn't be possible at all if we had to think about, for example, the semiconductor properties of gallium arsenide every time we type www.google.com into the web browser. Now that that's out of the way, it's time to introduce the IT terminology from the bottom layer up. So the first thing we need to do to create a network is to physically connect our devices together. In this context, the most common technology used to do that is Ethernet. Ethernet is defined by IEEE standard 802.3. IEEE is the Institute of Electrical and Electronics Engineers. Ethernet is the bottom layer for the purposes of this topic, but is really already built on top of many simpler, more general layers. And Ethernet itself actually defines multiple abstract layers. The first layer defined by Ethernet is the physical layer. And this includes the cabling, meaning the actual wires used to connect the devices together, which is most commonly for Ethernet either twisted pair copper or glass fiber. Ethernet defines things like the cabling requirements for specific data rates and maximum and minimum cable lengths. Ethernet also defines the signaling mechanisms, meaning the specific electrical or optical waveforms or frequencies or voltages or whatever that are used to transmit data, the bits, on the wire. An actual device that you might have seen or used that operates at the physical layer is an Ethernet hub. A hub is a device with multiple connection points, often called ports, used to connect devices together, and is basically a repeater that sends all data coming from one port out to all the other ports. And since only one device can use the wire at a time, because otherwise their electrical signals collide and become nonsense, the non-selective repeating behavior isn't as efficient as it could be because devices not involved in the communication have their wire occupied by irrelevant communication. The other layer that's defined by Ethernet is called the link layer. The link layer adds two pieces of functionality to our network. First, it deals with access to the wire by resolving the case when multiple devices transmit and the signals collide, and does this by specifying what the devices should do in that case. Secondly, it establishes a method to identify individual devices on the network by requiring each device to have an address called a MAC address. MAC, M-A-C, stands for Media Access Control, and it has nothing to do with an Apple Mac, that Mac being short for Macintosh, which is what they used to call their computers. A MAC address is a globally unique identifier in the hardware, globally unique meaning that no other device can have the same address. Each device on the network will see all messages that come in on the wire and will be able to ignore any that aren't addressed with its MAC address. To reference the abstraction concept I was talking about earlier, the link layer doesn't need to know the details of the physical layer. So from the link layer's perspective, the physical layer is abstract. It doesn't matter if the data is sent out as waveforms on a copper wire or pulses of light on an optical fiber or smoke signals or notes plucked on a guitar string. An Ethernet switch is a device that operates at the link layer. A switch can be somewhat smarter than a hub because the switch understands MAC addresses. It can learn which devices are reachable from each of the cables connected to it. Then, instead of broadcasting every message to every device like a hub would have to, the switch can read the destination MAC address and only send each message down the wire toward the destination device. A consequence of that is that multiple devices can communicate simultaneously across the switch as long as they are connected to the switch by different wires. Now, to motivate the next layer, it helps to notice that from Ethernet's point of view, there is only one network, which is everything connected to the wire. And of course, the hubs and the switches, which are just extensions of the wire. There is no concept of another network, and there's no mechanism within Ethernet to communicate with another network if one were to exist. This limitation has some notable consequences. One is that the network can only handle a limited number of devices before the physical layer is saturated with collisions, preventing any meaningful communication. A second limitation is that there's no way to have a private or secure network that can communicate with devices on a public or less secure network. And one more thing before I get to the next layer, circling back again to the abstraction idea, we can swap out Ethernet for different technologies that define the physical and link layers. A well-known example is wireless Ethernet, often referred to as Wi-Fi, which is defined by another IEEE standard, IEEE 802.11. 802.11 wireless Ethernet is very similar to 802.3 Ethernet, but uses radio as the physical layer rather than cables, and has a conceptually similar link layer using MAC addresses, but solving the additional problems that come with wireless communication. Other technologies that can be swapped in at this layer that you might have heard of are DSL and ISDN, and really pretty much anything that can allow devices to communicate with each other. Now finally to the next layer, which is going to solve our one network problem. This layer is commonly called the network layer. The principal technology at this layer is IP, which is short for Internet Protocol. IP has a mechanism for identifying multiple separate networks and also for allowing data to traverse from one network to another. In order to function on an IP network, a device needs several pieces of information. The first is an address, called, not surprisingly, an IP address. The IP address is basically just a number, a 32-bit number, but is most commonly represented as 4 numbers separated by dots. It's highly likely you've seen or used these before. The 4 numbers can each range from 0 to 255. An IP address encodes 2 pieces of information, the number that represents the network and also the number that represents the device on the network. The second piece of information a device needs is another number called a network mask, often called a subnet mask. I said before that the IP address encodes 2 pieces of information, and while the size of an IP address is fixed, the size of each piece is variable. The subnet mask tells the device which portion of its IP address represents the network and which portion represents devices on the network. So basically, the subnet mask indicates where to make the cut. For example, if your device has an IP address of 192.168.1.10 and a subnet mask of 255.255.255.0, something you might have seen before, this indicates that the network identifier is 192.168.1 and the device identifier on the network is the 10. So any device with an address that starts with 192.168.1, the network identifier, is on the same network, and any device with something else, like 192.168.0 or 77.26.53, is on some other network. This is a little bit difficult to explain in audio format, and it's not really that important to understand if you aren't responsible for designing or running a network. If you want a visual explanation of the subnet mask, head over to facilityscience.com and look at the notes for this topic. The next thing a device on an IP network needs is the IP address of a device that knows how to send stuff to a different network, at least one, but maybe more than one. This device that sits between 2 networks, possibly more than 2, and knows how to send stuff between them is called a router, or sometimes a gateway. A little side note, there's a device you probably have in your home or office that you and everyone else call a router that is actually much more than just a router, and I'll make that distinction later. Most devices will be configured with a default router or default gateway to which it will send anything that has a destination not on this network and for which no specific router is known. For example, our device with IP address 192.168.1.10 might be told that the default router or gateway is at 192.168.1.1. So if it wants to send something to IP address 8.8.8.8, it will notice that 8.8.8.8 isn't on the same network since it doesn't start with the 192.168.1. So the only thing our device can do is send the message to the router address 192.168.1.1 and hope that the router at 192.168.1.1 knows how to deliver the message. Most likely, the device at 192.168.1.1 won't actually be connected to the same network as 8.8.8.8, but will instead have to forward the message to another router, which may then forward it to another router until it finally reaches a router that is actually connected to the same network as 8.8.8.8. This layer, the network layer, is what makes the internet. If you can visualize a bunch of networks adjacent to each other, with a router at each place two or more networks touch, such that you can draw a path from any place to any other place by hopping through the different networks from router to router. You have visualized the internet. Each router in this interconnection doesn't have to know the layout of the whole internet work to help deliver data to a faraway place. It just has to know which routers it knows about might be a step closer to the final destination. You might also imagine in this scenario that one consequence of this interconnection scheme is that there might be multiple paths from a place to another place. So if some network or router somehow becomes unable to participate, there might be a way to go another way around to get the data where it needs to go. The reality is a little bit messier than this. There are a handful of other protocols or technologies that might be used in place of IP to make some of the connections, and some of the networks exist only to connect other networks together. Now, when you want to send data of some arbitrary size, IP divides the data into particularly sized chunks called packets. Each packet gets the destination address and the return address attached to it, just like putting a letter into an envelope with the addresses on the outside. After they're all chopped up and addressed, each packet is handled independently of the others. And since each packet of the message is handled by the routers independently, the individual packets of a particular message may take different routes to the destination, and some might not arrive at all. The process of routing packets by looking at each one and then forwarding to the router most likely to be closer to the destination is called packet switching, and is part of the genius that makes the internet work. Now, IPv4 versus IPv6. The IP addresses we've been talking about so far, that's the four numbers separated by dots, are IPv4 addresses. That's Internet Protocol version 4. A major limitation of IPv4 is that there are only around 4 billion possible addresses, which causes some problems. While 4 billion might seem like a pretty big number, there are more than 7 billion people on the planet, each of whom could have multiple devices, plus businesses and governments with their many devices. It's estimated that there are something like 20 to 30 billion devices connected to the internet. And I'll talk later about how this is possible with only 4 billion addresses. IPv6 is the newer standard, which, among other things, allows for many more addresses. Newer here means that it came out in 1998, so not that new as I'm recording this in 2019, but it's still not widely deployed. IPv6 allows for 2 to the 128th power addresses, which is enough for billions of addresses for every person on the planet. It's a very, very large number. Now, before we get to the end of the IP section here, I want to make it clear, in case it wasn't already, that IP doesn't know how to actually physically reach another device. IP doesn't know anything about cables or radio waves or electricity. It only knows about networks and routers and addresses. So a device communicating with IP needs Ethernet or something else that provides those capabilities to do the actual physical connecting. If you want to see how internet engineers entertain themselves, there's a spec for IP over a carrier pigeon. You can look up RFC 1149 if you're interested in that. Now, to motivate the next layer, when an IP device sends something to another device, it just chops up the data, puts the destination address on each piece, and throws it towards the nearest router. It doesn't actually verify the existence of the destination device. It doesn't make any effort to verify delivery of the message or have any means to retransmit undelivered data. Since, as I mentioned before, the nature of an IP network means that parts of the message are handled separately and might take different routes to the destination, the pieces might arrive at the destination out of order, and IP doesn't do anything about that either. So we need another layer. The next layer is called the transport layer. The main technology at this layer is TCP, which is short for Transmission Control Protocol. TCP is a connection-oriented transport mechanism for reliable, error-corrected, and properly ordered data transmission from the source endpoint to the destination endpoint. So what does all that mean? Connection-oriented means that before sending the data, TCP will make contact with the destination to make sure the destination device is actually there and reachable. This connection is made using the lower layer protocol, so IP, by sending basically, hey, are you there? Waiting for a response, yeah, I'm here, and then replying with, okay, here comes some data. This is technically known as a three-way handshake. Reliable means that the two ends will communicate to make sure that data gets delivered, and error-corrected means that if some data gets corrupted in transit, the destination will request retransmission of the data. And properly ordered means that TCP numbers all the pieces so that they can be reassembled at the other end. TCP and IP are often talked about together as TCP/IP or the TCP/IP stack. and it's called a stack because of the layers of protocols piled on top of each other. TCP uses port numbers to identify each particular application connection, allowing it to sort the mixed up stream of data coming in over IP and get everything to the right application, because IP is just a stream of data. There's no context for it. So if an application wants to connect to another application over the network using TCP, the application must specify the port number the application is using on the remote end. It's just a number. If an application wants to receive data over TCP, it must tell TCP which port it will be using. This is called listening on the port. And ports in TCP, like I said, are just numbers to identify each connection or application and shouldn't be confused with physical ports you would plug a cable into, such as on a router or a switch. TCP is just one example of a transport layer protocol, and maybe the most important one for the internet. Another prominent protocol at this layer, that would be used instead of TCP, is UDP, which is short for User Datagram Protocol. UDP doesn't do the error correction or reordering or reliable delivery of TCP. UDP is useful, for example, when the data transfer is time dependent, such as for live streaming audio or video or real-time gaming, when the extra overhead of TCP, all that checking and correcting, might cause the data to arrive too late to matter, or for situations when the application will handle its own error correction or whatever else, and the extra overhead of TCP would be redundant. So now we've gotten to a point where we have a way to communicate arbitrary data across our various networks in a reliable way. The next step is to use this communication mechanism to accomplish some specific tasks. For this, we have another layer, the application layer, which we'll call the top layer for the purposes of this topic. Protocols in this layer implement application-specific functionality using the services provided by the transport layer, so TCP or UDP. Examples of this are HTTP and DNS, FTP, Telnet, SSH, and even BACnet and Modbus can be used here. Two prominent examples that I want to talk about now that you probably use hundreds of times a day are DNS and HTTP. So DNS stands for Domain Name System and is used to translate names to IP addresses. You might have noticed that we just went through all that stuff that makes the internet work, from TCP down to Ethernet, and there's no way in any of that to connect to a place called facilityscience.com. The names we use to refer to things like websites are for humans. The computer needs an IP address to communicate with another computer across the internet, and DNS provides the means to translate names to IP addresses. I'm not going to go too deep into how this works, but if there's some demand for it, I can. The other application layer protocol I want to talk about is HTTP. HTTP stands for Hypertext Transfer Protocol, which is the mechanism used by web browsers and web servers to transfer web pages. HTTP defines how a web browser, so that's Google Chrome or Firefox or Edge or Safari, can make a request for a page to a web server like Apache or IIS or Node.js, and then also how the web server should reply. This is an important protocol because it enables a huge portion of the modern communication of information. There's also an important variation of HTTP known as HTTPS, which adds secure encryption to HTTP, enabling things like online banking or other forms of private communication. Network security is a whole topic by itself, so I won't go deep into that here. This application layer down to the physical layer, so Ethernet, etc., defines what is known as the Internet Protocol Suite. Now that we've gotten to the top of the stack, there are a couple things I want to circle back to. So I mentioned earlier that there are something like 20 to 30 billion internet-connected devices, but only 4 billion IPv4 addresses. One of the primary ways we are able to get around the IPv4 address-based limitation is called network address translation, usually shortened to NAT, N-A-T, NAT. So the first piece of this is that there are some blocks of IP addresses that are reserved for use in private networks and are designated as non-routable. This means that anybody can use these addresses on their networks without consulting with anybody else, but that they can't be used to communicate across the internet, meaning that internet routers will just drop them since there's no way to know for sure where they're going or coming from. These are the address blocks you might recognize from your home or office network. They're the ones that start with either 10 dot something, 172.16 through 172.31 dot something, or 192.168 dot something. You can look up RFC 1918 if you want the historical context. The point is that inside private networks, like the one at your home or office, you use an IP address like 192.168.1.100, and so does everyone else at their house or office. So we can just keep reusing these over and over again. The downside of this is that you can't use this address to access anything on the internet, because anything with 192.168.1.100 as the return address will be dropped by any reasonable router on the internet. And if it weren't dropped, there would be no way to get it back to you anyway, since your address is used by everyone everywhere. But somehow you can still get things from outside your network, so from the internet, on your home PC. So you have this thing on the edge of your network called a router, which is a term that still needs some clarification. When you send something over an IP network, you provide the destination address, so the network knows where to send it, and also your own address, so the device on the other end knows how to send a response back to you. Remember that a router is a device on two different networks, so it has a public IP address on the other network. Since you're using the non-routable addresses in your network, the router can't route things into your network normally, so it doesn't act like a router on the other network. Maybe you can think of it like a one-way router. On the other network, it just looks like another device. So here's the trick. When you send some data through the router to the internet, and your return address is one of those non-routable 192.168.something addresses, your NAT-enabled, that's Network Address Translation, router, removes your non-routable return address and replaces it with its own address that's on the other network, so the public address. It also keeps track of which device on the internal network the connection belongs to, so it can do the opposite with any reply that comes back. This is the translation in network address translation. The device on the other end of the connection doesn't send its reply back to your address. It doesn't even know it's communicating with you. It instead sends the reply back to your router's address, and the router forwards the response back to you. With this mechanism, everyone can have tens or hundreds or thousands of devices on the internet, but each network only uses up one IP address. Okay, now we can circle back to the term router and how it relates to that device you have in your home that you might have gotten from your ISP that we call a router. The device is a bit more than a router. There is a router inside, which is connected both to your internal network and also the internet, or more precisely, your ISP's network. This device is also a convenient place to put all the other infrastructure pieces you might need in order to have a functional network. So your home router is a router, but is also probably an Ethernet switch and a wireless access point. It additionally provides firewall capability to control what can get into and out of your network. It does NAT, so the network address translation, which I talked about earlier, and provides DHCP for your network. And DHCP, which I didn't cover before, stands for Dynamic Host Configuration Protocol. Previously, I mentioned a bunch of stuff a device would need to operate on the internet, so like an IP address, a subnet mask, a router addresses, DNS server addresses. So DHCP is a mechanism to enable automatic configuration of all those things so that we don't have to enter them all manually on every device we add to the network. And this is another thing that will be included in your router that you have at your home that's actually way more than a router. So I'm going to end this here. There's a lot more relevant internet-related terminology, but I think this is dense material and I might have gone on too long already. If you have any questions or comments on this or a suggested topic, you can send email to podcast@facilityscience.com. Before I go, I want to thank all the facility managers and engineers and technicians and mechanics and cleaning crews and everyone out there who helps to keep the lights on and the water running and to maintain the comfort and safety of our incredible civilization. I hope you find this helpful. Thanks for listening.